Now that we've talked quite a bit about vertical asymptotes and most recently horizontal asymptotes, we are prepared to graph a rational function from scratch. So we're going to walk through this example very carefully using the knowledge we've already discussed and then a couple new ideas. So let's work on graphing the function f of x equals, and we'll make it a fairly messy one if that's all right with you. So x squared plus 5x plus 4 in the numerator divided by x squared minus 9. That's a pretty good looking rational function. And everybody's approach to graphing could be a little bit different, but I'm going to go ahead and find the vertical asymptote and domain as my first step. Then I'll comment on the horizontal asymptote. Then I'll probably find some x and y-intercepts and then plot those points and make the graph. So that's the order that I'm going to try moving through this problem in. You may prefer a different order, but again, let's just kind of give ourselves some structure in case graphing rationals is brand new to you. So let's start with finding the vertical asymptotes and the domain. So to find the vertical asymptotes in the domain, we are focused really on the denominator, which in this problem is x squared minus 9. If we set the denominator equal to 0 and solve, the resulting solutions will be the vertical asymptotes. So you could solve this one a couple different ways. Maybe just for kicks, I'll go ahead and factor this one. I know often we would use just the square root property, but let's go ahead and factor just for a change of scenery. So this will give us two different vertical asymptotes. We're going to find either x is equal to -3 or x is equal to +3. And those would be the two vertical asymptotes for this one. Finding those immediately sheds some light on the domain of the function. So if the vertical asymptotes are -3 and 3, the domain will be everything but those values. And today we can write domain as either all x such that x does not equal to -3 or 3. That would be our set builder notation. Or in interval notation, I would say -infinity to -3, unioned with -3 to 3, unioned with 3 to infinity. So it takes 3 different intervals to jump over our two values we can't include. So that would be the domain corresponding with the vertical asymptotes for this function. So hopefully that feels pretty good so far. Let's go ahead now and comment on the horizontal asymptote. So for the horizontal asymptote, we talked through three different possible cases for horizontal asymptotes, and basically it's related to the relationship between the degree in the numerator and the degree in the denominator. So let me go ahead and write our function one more time so we can see it a little bit more readily. And I want us to focus on the degree of the numerator and the degree of the denominator. So I think you all would agree that the numerator's degree would be 2, and the denominator's degree would likewise be 2. So we're falling into what I described in our last video as case 3. Again, the naming of the cases is arbitrary, but that means that the horizontal asymptote, is just the ratio of the coefficients. Because the powers are the same, we can just grab the ratio of the coefficients of those powered terms, and we find in this example that the horizontal asymptote is going to be y equals 1. So just like a vertical asymptote has an equation x equals a number, a horizontal asymptote has an equation y equals something. Cool. So basically what we found so far is we found lines to avoid, right? So even just with the information on the screen so far, I could begin discussing a graph with you all. Let's go ahead and do that. Let's just get these vertical and horizontal lines plotted so that we feel like we're making progress, and you may already have some intuition about what the shape of this graph could look like. So to prepare for our ultimate graph here, I'll go ahead and get in the vertical asymptotes, which we found to be at +3 and -3. And then we'll get in the horizontal asymptote. Again, there's never more than one of those, and we found it to be at y equals 1. So here's our vertical asymptote at x equals -3. Another vertical asymptote at x equals +3. and horizontal asymptote at y equals 1. Cool, so we're just starting to get a little feel for our function. Now, friendly reminder, your function will never ever cross the vertical asymptotes, but it is okay for it to cross the horizontal. So the horizontal asymptotes typically are more about the end behavior of the function. So in this example, it's likely that the function will cross through the horizontal asymptote kind of in the middle of the graph. So just keep that in mind. Sometimes we think it can't touch ever, but it is okay to cross through a horizontal asymptote. But just using asymptotes, we don't have a lot of information about the shape of our graph, so let's go ahead and find a little bit more information. One thing I'll ask you guys typically to find will be the intercepts. So let's start by finding the y-intercept, just to get another point, or really our first point to plot for this graph. So how do we find a y-intercept? Remember, a y-intercept means x is equal to 0, right? So that means into our function, we can insert 0. So f of 0 will be, and I'll just show plugging in. I think I still have the rule of the function up there where we can see it. I'm going to show plugging in 0 for all of the x terms. So x squared plus 5 times x plus 4 divided by x squared minus 9. So I'm plugging in 0 for x to find the corresponding y, and that will generate an ordered pair for us. So if we simplify, it looks to me like we're getting back, what would it be? Just 4 in the numerator and negative 9 in the denominator. So negative 4/9. So as an ordered pair, that means that the y-intercept is, I'll just write it in orange here. It means we have the point 0, negative 4/9. So that just starts to help give us a bit more information. And why don't we go ahead and plot that point since we found it. So when x is 0, y is negative 4/9. So again, it's kind of a rough estimate. That's somewhere close to a half, a little less than a negative half. So when x is 0, y is somewhere in there, right? So we feel like we have maybe a little bit more information about our graph, but still not too much. So let's try the x-intercepts. Or intercept. We'll see what we can find. So let's find x-intercepts, at least if they're easy. So remember, with your y-intercept, you'll never have more than one. You can have more than one x-intercept because for the y-intercept, if you had more than one, it wouldn't actually be a function, right, from the vertical line test. So to find the x-intercepts, that means we are setting y to equal 0. So x-intercepts can be a little bit more challenging. It means we're setting the function we were given equal to 0. And again, our given function was this x squared plus 5x plus 4 over x squared minus 9. Now, when we have a fraction equal to 0, we have to ask ourselves what matters, the numerator or the denominator? And I think you all would agree that if you have a fraction set to 0, if the numerator equals 0, the result of that fraction would be 0, right? So what we're saying here is that 0 divided by any number, any non-zero number, would be 0. So what that helps me know is I really just need to focus on solving when 0 equals just the numerator, which is the x squared plus 5x plus 4. So I don't need to worry about the denominator right now. Setting the denominator to 0 would find where the function is undefined, and we've already done that for the vertical asymptotes. So to finish solving this, I would probably use the technique of factoring. So two numbers that multiply to 4 and add to 5 sound like 1 and 4. So that means I'm getting x equals negative 1 and x equals negative 4 when we solve this. So that means as ordered pairs, we do have two x-intercepts. One of them is negative 1, 0, and the other one is negative 4, 0. So this just gave us two more points that we can plot, and having two more points will help us feel like we have a better understanding of our graph. So a moment ago, we plotted the y-intercept. Now let's go plot these two x-intercepts. So we need a point at -1, 0, so that would be right in here. And our other x-intercept is going to be to the left of this vertical asymptote, so out at -4, we'll have another x-intercept. Cool. So graphing rational functions is not the easiest because just with the asymptotes and the points that I've plotted, it may not feel super clear how to sketch in the function. I would argue, though, that you probably could feel somewhat comfortable sticking in this piece. We know rationals are made up of pieces, and we know that the function avoids asymptotes, especially with the end behavior. So I think this piece here on the far left would seem intuitive. We need to make sure we pass through the x-intercept at -4, 0, and we need to slide right along the vertical asymptote but not touch it. And similarly, we approach the horizontal asymptote. So what I might do from here is maybe plot a couple more points. For example, on this far edge of the graph, it may not feel clear yet whether we're going to have a piece up here like this, or if we're going to have a piece more down here like this, right? You might be wondering which of those two things could happen. So based on this example, an easy way to distinguish where that piece goes is maybe plug in a value like x equals 4, just to see if the output is above or below the horizontal asymptote. So I'm going to go find another point. And this is where my process could look a little different from yours. So I'll pop over here and let's just say find another point to get a little bit more better description. So another point, let's plug in 4. Let's just plug 4 in. So f of 4 means plug in 4 for all the x's in this function. So that means, let's see, our original again was x squared, so 4 squared, plus 5 times x, so 5 times 4, plus 4, divided by x squared, so 4 squared, minus 9. I'm just plugging in 4 for all the x's. If we clean up a little bit in the numerator, I've got a 16 plus a 20 plus a 4. In the denominator, I've got a 16 minus 9. So the numerator, let's see, 16 plus 20 is 36, plus 4 more makes 40. 16 minus 9 sounds like 7. So we just found the ordered pair 4, comma, 40 over 7. This is going to help me know again whether my function piece in that part of the graph is above or below the horizontal asymptote. So 40 over 7 may be a little hard to think about graphically. Feel free to punch that in to get a rough decimal. So that would be about 5.7. So let's plot that point. When x is 4, the y value is about 5.7. 3, 4, 5, 6. So we're somewhere kind of way up here, right, for that point. That helps me know then without much doubt at all that that piece of the function will appear above the horizontal asymptote. So this is definitely a sketch. It's far from perfect, but I'm going to have a piece coming in kind of like this. Now we have the two ends of our graph in place. Now it's just the middle part that we're left with. So probably connecting these points seems natural. We're always going to butt up against our vertical asymptotes, so approaching that as I just drew is about the only option we have. Similarly, on this side, I can't really go back towards the other asymptote because if I did that, it wouldn't be a function. So this other end has no other choice but to start approaching its asymptote as well. So getting used to the behavior of rationals can be a little funky. This example was complex enough that it should handle most of the problems we'll be doing together in our course, but just always holler if you'd like to see another example. So that's a little bit of information about graphing rational functions by hand. Don't forget to check your work in Desmos.